All right, let's practice a little bit about finding bases for null spaces and column spaces of a matrix. So the basis should be as simple as possible. And of course, the elements in the basis have to be linearly independent. So the best thing to do is to practice. Let's say we have a matrix 3, 2, 1, 1, 2, 3, 4, 5, 6. And we want to find the null space of this matrix. And then we will also find the column space of this matrix. So there are two things that we want to find: the null space and the column space. So the null space is the set. Well, actually, what we want is a basis for the null space. The null space is the space of matrices x, y, z. So when we multiply, we end up with, of course, 0, 0, 0. And we could solve the system of equations, or we can simplify this by elimination and then end up with a system of equations that is going to be equivalent to this one. And then we can obtain the solution from there. So again, before we forget, let me just write down that we are looking for the null space. So finding null space. Okay, so let's reduce this. For instance, we can take this guy and subtract the first row. And so 4 minus 3 is 1, 5 minus 2 is 3, 6 minus 1 is 5. While we do that, we can also subtract from this row this one. So I'm actually doing two steps in one. 3 minus 1 is 2. Just to simplify that a little better, 3 minus 1 is 2. 2 minus 2 is 0. I don't know if that's going to be too helpful to have a 0 this early into the problem. And then 1 minus 3 is negative 2. But that means that we leave this alone. 1, 2, 3. So we are reducing. It's probably a good idea to keep record of what we are doing. So, and especially if you're writing this as part of, so we're just taking the matrix. We're not actually changing the system of equations yet, although nothing on this part is going to change anyhow. So again, we took the third row, subtract the first row, and then we took the first row after that and subtracted the second row. So let me double check. 1, 3, 5, and then 2, 0, negative 2, and then 1, 2, 3. I don't think there was really necessary to do that. See, I'm picking this guy as our pivot, although I guess I could have used this one. Maybe I should have, but that's all right. So I'm going to choose this guy as my pivot, and we're going to subtract from the first row twice the last row. So take row 1 and take away 2 times row 3. And of course, that is going to give us 0 in the first row. That's the whole point. But then we have negative 6. And then negative 12. And then from the second row, we can subtract the third row. And that's going to give us 0, negative 1, negative 2. And then we can leave the last row alone. 1, 3, 5. And then we can arrange the rows. So continuing the process down here, we're going to take row 1 and exchange it with row 3 so that the pivot goes on top 1, 3, 5. Keep the second row alone or as is. And then the last row is going to be 0, -6, -12. Boy. So those two rows are the same really, because if we divide by -1, we end up with 1 and 2. And if we divide by -6, we end up with 1 and 2. So those two are the same. Let's formalize that by actually writing down -1 times row 2. And we're also going to divide by -6 row 3. And that's going to give us 1, 3, 5. 0, 1, 2, 0, 1, 2. And then we can take away from, because we really want to simplify this as much as possible, we can take away the 3 using row 2. Since we already have zeros here, that is not going to affect that pivot, initial pivot. And so we're going to choose this to be our pivot. So take row 1 and subtract 3 times row 2, while we take row 3 and take away row 2. And that's going to give us 1, 0, and -1, 0, 1, 2. And then when we subtract, we end up with zeros. Okay. So that means we have 2 pivots. We don't have a pivot here. And that means that the rank is 2. The rank being 2, that means that there are 2 columns that are linearly independent, as well as 2 rows that are linearly independent. And then we have one free row, the one that, rather, one free column. So let's recall that a free column is the one that has no pivots. So pivot, those are not free, but this one is free. And that tells us that the null space will be one-dimensional. So rank of this matrix is 2 because there are 2 columns with pivots in it. And then there is one free column. And then we're going to use this free column to, well, actually, to figure out the null space. We're going to use this matrix. So this means that x minus z, and z is the free variable. So z can be anything we want it to be. So x minus z equals 0. Again, if we put back the x, y, z equals 0, 0, 0, which is our initial equation, we have not changed the equation or the solution set because we are doing row operations, which means adding, subtracting, or rearranging rows, which doesn't really change the nature of the solutions. The solutions still are the same. In other words, if you have a solution here for this system, then the solution is going to be valid here and here and here and here and here. So again, what we are saying is that x minus z, no y and minus z is equal to 0. Well, when we multiply x minus z is equal to 0, which means that x is negative z. And then here what we have is that y plus 2z, y plus 2z is equal to 0. And nothing, well, 0 is equal to 0. So the z can be anything it wants to be because we're going to multiply by 0 anyhow. And so what this is telling us is that x is z when we move this over, and that y is negative 2z. Yeah. So the, the null space, the solution to this equation, which is, well, all the solutions to this equation, which is what we are looking for the null space, is x, y, z, will be equal to, well, x is z, y is negative 2z, 2z, and then z can be anything. So there's no restriction. This doesn't bound z to anything. It bounds x because we're claiming that z can be anything, but it doesn't bound z to anything. So z can be itself. Z can be anything. Now, if we factor out the z, yeah, then we have the vector 1, negative 1, 1. Let me double check to convince myself that actually we get 0, 0, 0. Let's write the original problem. The original problem has 3, 2, 1, 1, 2, 3, and 4, 5, 6. And let's multiply with this vector. If you multiply with a scalar here, the scalar will factor out. So if we end up with 0, that scalar multiply with 0 is still going to give us 0. So that if we get 0 in the multiplication, that this extra z is not going to matter anyhow. But let me double check that we actually get 0, 0, 0. So that is 3 minus 2 is 1, plus 1 is 2. Whoa. 3 minus 2, that should be a negative 1 for this to work. So let me record what I have. 3 minus 2 is 1, plus 1 is 2. But we're supposed to get 0, 0, 0. 1 minus 2 is negative 1, plus 3 is 2. 4 minus 5 is negative 1, plus 6 is 4. So this is definitely wrong. Okay, but I just realized where the mistake is. The mistake is when I factor out the z, I neglected to put here a 2. And so this should be 2 as well. So I'm fixing it, and let's double check now. 3 minus 4 plus 1, 0. 1 minus 4 plus 3, 0. 4 minus 10 plus 6, 0. Okay, so it is a good idea because I did make initially a mistake here when I factor out the z and I didn't put the 2. I left it as negative 1. So it is a good idea to double check that actually this vector is part of the null space. Now, if we multiply by any constant or any variable, we will end up with that variable being factored out, and so we still end up with 0, 0, 0. So that means that this is the only element in the basis of the null space. So let me write down an answer. So the basis, or a basis is probably better because there are many bases. A basis of the null space of the matrix 3, 2, 1, 1, 2, 3, 4, 5, 6 is where's the 1, negative 2, 1. Now remember, a basis is a set of linearly independent vectors that generate the space in question. So this generates the null space. And it's pretty simple. I don't think we can simplify it anymore, because a way to simplify it would um, have to have a zero. But if one of them is zero, that means all of them are zero, and that generates the wrong null space. So this is the basis that we are looking for. Okay, now let's focus on the column space generated by those columns. All right, so let's write down 3, 2, 1, 1, 2, 3, 4, 5, 6. And we want to find a basis. Let's just write it this way. So we want to find a basis, a basis for the space generated by the columns, of this matrix. What I Well, so there's a column, a column, a column. And what we want to do is find any redundancy. We want to simplify, and also, I'm going to sneeze. Excuse me. Excuse me. So we want to reduce this matrix, but by columns, not by rows, because we want to detect any redundancy. So what I'm going to do is just do that, reduce by column. So instead of doing row operations, I'm going to go ahead and do column operations instead. So I'm going to pick this as my pivot, and I'm going to use that to get rid of the 3 and the 2. Again, we're going to reduce horizontally as opposed to reduce vertically. So this is a little different. All right. Yeah. So we will reduce the columns. So X, Y, Z. We want to reduce the columns. Yes, we do. Okay. Boy, this is interesting to me. So take the first column and subtract 3 times the third column. So column 1, take away 3 times column 3. So now we're doing column operations. 3 minus 3, 0, that was the point. 1 minus 9, negative 8. 1 minus 9 is negative 8. 4 minus 18. 4 minus 18 is negative 14. Well, let me double check that again. 3 minus 3, 0. 1 minus 9, negative 8. 4 minus 18, negative 14. Okay. Then we're going to take away from column 2 twice column 3. 2 minus 2, 0. 2 minus 6, negative 2. 5 minus 12, negative 7. 1, 3, 6. I'm going to flip those two. We're going to exchange column 1 with column 3. 1, 3, 6, 0, negative 2, negative 7, 0, negative 8, negative 14. Okay, I want to end up with a 1 here on this pivot position. So we're going to, that's going to mess up the 7. I'm trying to think if we can get a 1 here with those two, and we cannot really. Yeah, I think it's probably best to divide by Now, are those two multiples of each other? Times 4 gives us that. Times 4, no, they're not multiples of each other. That is interesting. So anyway, let me double check that this is accurate. 1 minus 3 minus 1, 3 is 0. 1 minus 9, negative 8. 4 minus 18, because we're subtracting 3 times. 4 minus 18 is negative 14. 2 minus 2, 0. 2 minus 6, 2 minus 6 is negative 4. 2 minus 6 is negative 4. And I'm going to tell you why I thought there was a mistake. 2 minus 6 is negative 4. And then 5 minus 12 is negative 7. Yeah, and now those two are multiples of each other. The reason why I was suspecting there was a mistake at this stage of the game is because the ranks, when we row reduce or column reduce, have to be the same. And in the example one, we noticed that the rank was 2. Had those two not been multiples of each other as far as columns go, then the rank wouldn't be 2 anymore. It would be 3. And the ranks have to remain the same, whether we do column reduction or row reduction. The rank has to remain the same. Even if we don't have square matrices, the rank stays the same. Yeah, because the pivots stay the same. Well, yeah. So this guy should be negative 4, not negative 2. All right. And that means we can get rid of this very easily by adding or subtracting twice this guy. So we can do C3 minus twice C2. So we're going to end up with 1, 3, 6, 0, negative 4, negative 7. And now we're going to subtract twice this. So 0, 0, 0. And then we want to have pivots here so that we can get rid of this. Ideally, we want to have as many zeros as possible. So because that just makes the vectors much easier to follow and to understand. So first we're going to make this a 1, this pivot. So we're going to take the second column and multiply it by 1 over negative 4, the second column. So we still have 1, 3, 6, 0, 1, and then 7 over 4, because we are dividing by negative 4, and then leave the last column alone. We're not going to touch this column anymore. So then we can get rid of this 3 by subtracting 3 times the second column. So take the first column and subtract 3 times the column 2. And that's not going to mess up this 1 because we got zeros across. So we have 1, 0 because we're taking away 3 of those. This is going to be a little more messy because we're going to take away 3 of those. So 6 minus 21 fourths. I'm just going to take a piece of paper and do that computation on the side. 6 minus 21, 6 minus 21 fourths, that's equal to 24 fourths, because that's what 6x minus 21 fourths, and that is 3 fourths. That's interesting. 3 fourths, and then we have 0, 1, 3 fourths, 0, 0, 0. Okay, so by doing this column reduction, we got rid of redundancies. See, these two columns were the original 3 columns were too many. What that tells us is that one of them, this one, can be written as a linear combination of those 2. One of them is redundant. Now, how can I tell that one was the redundant one? Because this first one, because there was a switch between 1 and 3, and then the third one is the one that became 0. Okay. So first, let me write down the answer, and then we can elaborate on why this is correct. So first of all, the question at hand was to find a basis for the space generated by the columns. So the basis will be the 2 vectors 1, 0, 3, 4, and 0, 1, 3 over 4. There. So those are the 2 elements, nice elements, that are going to generate the whole space generated by those 3 columns. If that's so, that means that those 2 are linearly independent, and they generate those 3 guys, those 3 columns. So first of all, let me write the answer. So this is the end of the problem, okay? To find a basis, here we have it, a nice basis, because there's zeros. So find I'm going to call it for now nice basis, because it is reduced. We could have ended up here with, we could have stopped here once we got this, because there's no way to reduce any farther. This is a pivot, and there's no more pivots. But this is even better. So this is the one we want to end up with, because it has zeros in it. So how do we know those 2 are linearly independent? Because we cannot reduce this anymore. If we, yeah, it is by the process. But let's prove it differently. Okay, because we want to practice how to prove how things are linearly independent. So let's answer this question. Are this vectors, and what by that I mean the vectors in this set, vectors linearly independent, question mark. Well, let's see. Pretend C1 times 1, 0, 3 over 4 plus C2 times 0, 1, 3 over 4 is equal to 0, 0, 0. Assuming this should lead us to the only possibility in which C1 is 0 and C2 has to be 0. And actually, we can start seeing that almost right away. So when we multiply C1 into this vector, we get, okay, let's just write it down. So C1 times 1 is C1. C1 times 0 is going to be 0. And so C1 times 3/4 is 3/4 C1. And then we're going to multiply through here with C2. Sorry about that. That's just nothing. There. So 0 times C2 is 0. 1 times C2 is C2. And then 3/4 C2. And that should be still 0, 0, 0. So we're multiplying through to see the nature of C1 and C2. Now, we don't necessarily have to do this every time. If we did our steps correctly in the column reduction, then we should be okay. But I like to double check just to be sure. Then we have C1 plus 0. So that is C1. 0 plus C2, that is C2. And 3/4 or 3/4 C1 plus 3/4 C2, well, that is 3/4 C1 plus 3/4 C2 equals 0, 0, 0. But that means that C1 has to be 0 and C2 has to be 0. And that those two have to be 0. But if those two are already 0, then multiplying by 3/4 and adding them together, it's still going to give us 0. So C1 has to be 0 and C2 has to be 0. Thus, the vectors 1, 0, 3/4 and 0, 1, 3/4 are linearly independent. Okay, so in order to have a basis, we have to show that the vectors involved in the basis are linearly independent. We also have to show that they generate the space. Which space? Well, we want to find a basis for the space generated by those three columns. Let's call these columns V1, V2, and V3 for now. Okay, so V1, V2, V3, whoops, are going to generate the column space of the matrix. Okay, what I claim is that the span of these new vectors, let's call them W1 and W2. So W1 and W2 generate the same column space. Same column space. Okay, so one way to go about showing that those two generate the same column space is to show that those three vectors are generated by those two. If we do that, then we are set. See, if those two generate V1, and these two generate V2, and these two generate V3, then certainly these two generate that space because those three generate that space. So those three generate that space. But if we find two that generate those three, that means that those two also generate this space because we're talking about linear combinations. Okay. Yeah. So this space is the linear combination of all those vectors. But if those two generate those, then every linear combination of those three is also a linear combination of those two, which means that one of those is redundant, at least one of those. And not only that, we can actually come up with vectors that are even simpler because it doesn't, what we didn't just cross one off. We actually came up with new vectors. Yeah. Occasionally, we can just cross one off. In fact, we should be able to, I think. I'm not positive, though. I have to check that out. Anyway, if we can just cross one off, that would be a good thing to check. But anyway, so take the first column vector, 3, 1, 2, rather 3, 1, 4, 3, 1, 4. And now the question is there a linear combination? I'm going to use C1 and C2. Maybe not. D1 times 1/3/4 and D2 times 0/1/3/4 that gives us 3, 1, 4. You know what? Based on the previous example that we finished up here, where we found out that this guy equaling this causes the C1 to be 0, and this one equaling that causes the C2 to be 0, can be used here because, I mean, if we start looking at this and staring at this enough, we're going to say, okay, we're going to end up with d1 times 0 plus, rather, d1 times 1 plus d2 times 0. What that's going to be just d1 equals 3. So the conclusion of this equation is that d1 is equal to 3. Okay, d1 times 0 is 0 plus d2 times 1 is d2, which should be equal to 1. So d2 is equal to 1. And that linear combination will do. Let's double check. So 3 times 103 over 4 plus 1 time 013 over 4 should give us 314. But let's see if it's true. 3, let's do it row by row. 3 plus 0, 3. Yeah. 0 plus 1, 1. Yeah. 9 fourths plus 3 fourths is 12 fourths. That doesn't work, does it? 3/4. That didn't work as nicely as I thought it would. Let me double check my column vector. 3, 1, 4, because we're still working with the same matrix. 3, 1, 4. That gives us 3, not 4. 3 is 9, and 3 is 12, divided by 4 is 3. Let me check. Yep, I found a mistake. Boy, this is not my best video. I noticed that back here, as I was looking back, this is 7 over 4, and that should be 7 over 4, because when we subtracted, this was 24 over 4 minus 21. Yes, we end up with 3 over 4, but inadvertently, that turned out to be also I put down inadvertently 3 over 4, but that remains as 7 over 4. So this guy should be 7 over 4. And so it does not hurt then to check, because then I can fix the mistake. The linearly independency does not change, because if those two are forced to be 0, so this would be 7. And looking back at here, we end up with 7. And since those two are already 0, that does not affect the fact that this would be 0. 7. Okay. So the linearly independency was not affected. We still end up with C1 and C2 equal to 0. So our conclusion that those two are linearly independent still checks. Here, this should be 7. And so is this. Boy, good thing we are checking then. And now we have 9 over 4 plus 7 over 4, 16 over 4, not 12. So let me cross that off. But by doing this, I realized there was a mistake on the previous page. 16 over 4 is indeed 4, but after fixing this, and it checks. Yeah. So we want to make sure that those two indeed generate those 3. Now, we only check this part that those two generate the first column of the original matrix. But now that I realize I made a mistake here, I need to check that those two vectors generate the second column as well as the third column. Notice that it's easy. Once you have as many zeros as possible. It's easier to figure out the linear combination that works. Okay, so next, I'm going to use two new letters, C, D. I'm going to use E, just going in the alphabetical order. So E10 3/4 plus E2 0 7/4. Is there a linear combination that gives us 2, 2, 5? 2, 2, 5. Well, since we got zeros, that means that E1 should be 2 and E2 should be 2 as well. And let's check. 2 times 1/3/4 plus 2 times 0.17/4. Well, let's see, that's 2 plus 0, 2. 0 plus 2, 2. 6/4 plus 14/4. That's 20/4. Yep, and that's the same thing as 5. So it checks. 2, 2, 5. I mean, we have to simplify, but it does check. Okay, next. Can we generate 1, 3, 6? And I'm gonna, anticipating how this is working out, 1 times 1/0 3/4 plus 3 times 0.17/4 should generate 1, 3, 6. Let's see. Well, yeah, we get the 1. That works. 1 times 0 and 3. Yep, that works. And then this is the main one, or the one that is more crucial. 3 and 21 is 24/4, 6. Yep. All right. So this is what's going on. 1/0 3/4 and 0.17/4 generate 314, and they generate 225, and those two generate 136. So a combination gives us this. A combination gives us, a combination of those two gives us this. A combination of those two gives us this one. So if those two can generate that, then those two can generate the space generated by that. So there's a space generated by those columns. Let's call it, I don't know, V. And since those three generate this space, and those two generate each one of those three, that means that those two generate this space. Yeah, so that's how we obtain a base. Okay, let's do a second example. Well, even though these are two examples, I use the same matrix. I want to use a new matrix, a different matrix. But I'm going to show you how I'm going to come up with a matrix. So building a matrix of rank 1. And I read this, I didn't come up with this myself. I read this in a book by Strang. So I don't know if he, I don't know, but I just read it there, and so I just want to give credit to where I read it. Okay, so we're going to multiply a row with a column, so 1 by 3, 3 by 1. Yep. So I'm just going to come up with 1, 2, 3, 4, 5, 6, and that's going to give us a 3 by 3 matrix, because, oops, the other way around. This is a 1 by 1 matrix, not this one, because this is 1 by 3, and then this is 3 by 1. So they do multiply out, and we get a 1 by 1 matrix, but that's not the one I wanted. So I'm going to reverse those two, 4, 5, 6, 1, 2, 3. There we go. And that's going to give us a 3 by 3 matrix, 3 by 1, 1 by 3. So the multiplications are very short. It's just 4, 8, to 12, 5, 10, 15, 6, 12, 18. Interesting. Anyway, so I'm going to use that as example 3. We want to find the null space by that. Actually, we mean find a basis for the null space, a nice basis. That's what I mean by that. A set of linearly independent vectors that generate the null space. This example is different because this example has rank 1, as opposed to the examples that we just did that have rank 2. All right, so we're going to start with the matrix for a 12, 5, 10, 15, 6, 12, 18. I'm going to row reduce it. So I guess we can divide the first row by 4. So take row 1 and multiply it by 1 over 4. And that's going to give us 1, 2, 3. And then we have the other rows as is. You know what? We can reduce the 2. 1 multiply by 1/5, the second row. Multiply the third row by 1 over 6. So we're going to end up with 1, 2, 3, 1, 2, 3. That's going to make 1, 2, 3, 1, 2, 3. So we're doing row operations, and then we can take second row and subtract the first row, and the third row minus the first row also, and that's going to give us 1, 2, 3, 0, 0, 0, 0, 0, 0. So we row reduced it very quickly. Now this has only one pivot. This column has no pivots because the pivot should be the first element that is non-zero on that, and this is the first element that is non-zero. So this cannot be a pivot. So there's only one pivot in the whole matrix. Consequently, those two are free columns. And that means that z and y can be anything they want it to be. X is bound by y and z. And this is corresponding to the rank. So the rank is 1. Rank is 1 because there's only one column with pivots. Now, let's see what this says. This says that x plus 2y plus 3z is equal to 0. Now, mind, we're looking for the null space, so we're looking for all the x, y, z's that multiplied on the right with this matrix are going to give us the vector 0, 0, 0. Okay. But that just says, let's write this out. So 1, 2, 3, 0, 0, 0, 0, 0, 0 times x, y, z equals 0, 0, 0 implies that x plus 2y plus 3z is equal to 0. See, x plus 2y plus 3z equals 0. And then 0 equals 0 equals 0, which doesn't add any information. And that means that x has to be the opposite of 2y minus 3z. And that means that y and z can be anything they want to be. In other words, x, y, z, for this to work, has to be negative 2y minus 3z, and y can be anything and z can be anything. This step is very, very important, guys. And we can split it up into y's and z's, negative 2y, y, nothing, because only y's in this, plus only z's on the other, negative 3z, no z here, and one z there. And we can factor out the y, and we have negative 2, 1, 0. Factor out the z, and we have negative 3 and 0 and 1. That's a z. Okay, so every xyz that causes this product to be 0 has to be written in this form, which tells us that the basis for the null space contains the elements negative 2, 1, 0, comma, and negative 3, 0, 1. And there we have it. We have a nice basis. By the way, this also tells us that we have dimension 2. How do we know they're linearly independent? They're linearly independent because a combination of this plus a combination of that equaling 0, 0, 0 will have to force the second coefficient to be 0. So, and that also forces the first coefficient to be 0. Let's write it down. Okay, so first of all, we finished the problem. There is the answer. Are they linearly independent? Li question mark. Well, let's have a linear combination. Negative 2, 1, 0, C1 plus C2 times negative 3, 0, 1. Equaling 0, 0, 0. What does that mean? Okay. When we multiply C1 times negative 2, we get negative 2 C1 plus negative 3 times C2 equals 0. Okay. But then on the second line, we have C1 times 1 plus nothing equals 0. Okay, that's already progress. That tells us that C1 has to be 0. And on the third line of this equation, we have 0 times C1 is 0, plus 1 times C2 equals 0. Because this setup forces C1 and C2 to be 0, the two vectors involved are linearly independent. So yes, comma, negative 2, 1, 0, and negative 3, 0, 1 are linearly independent. How do we know they generate the null space? Oh, that's not too difficult to show. Let's go back to the original matrix. The original matrix was or is 4, 5, 6, 8, 10, 12, 12, 15, 18. If we multiply by any of those two, we better get 0, 0, 0. But so let's double check. 1, 0. And then we're going to multiply that same matrix, the original one, with the other vector, and we better get 0, 0, 0. So let's see, 8 negative plus 8 plus 0, 0, checks. Negative 10 plus 10 plus 0, checks. That's a 6. Negative 12 plus 12, plus 0 checks. Now, once you start looking back, those do make a lot of sense. Negative 12 plus 0 plus 12, 0. Negative 15 plus 0 plus 15, 0. Negative 18 plus 0 plus 18, 0. Check, check, check. The only thing that we could be missing is that maybe there is a third vector that does that. We found two that are linearly independent. What if there is one more? The only way to know whether there is one more or not is by double checking our process and making sure that we did not make a mistake, because that has to do with the rank. If we end up with a rank of 1, that means that there are two free columns, which tells us that we will end up with two vectors in the basis. It is pretty straightforward that we do end up with two. In fact, I read in Strang's book that when you build a matrix this way, we will end up with a rank of 1. So yes, a rank of 1 with 3 columns means that we have 2 free columns, which means that the null space has dimension 2, which means that the basis has 2 elements in it. Let's find a basis for the column vector. So example 4, find basis for the column space of the matrix. I think I already memorized it for a 12, 5, 10, 15, 6, 12, 18. Okay, now remember, guys, the way we go about doing this is by simplifying the columns, by doing column operations. That's gonna get a little messy to get a 1. It's easier to get zeros using the 4. I'm gonna do that. I'm gonna leave figuring out 1s last. So I want to eliminate that 8 and that 12. And that shouldn't be too difficult because 4 is a factor of 8 and 12. So we're gonna take the second column, column 2, and take away twice column 1. We're gonna take column 3 and take away 3 times column 1. So the first column is not changed under this column operation. So take away 2 of those, take away 2 of those from 8, 2 of those from 10, 2 of those from 12, and we end up with 0, 0, 0. Take away 3 of those, oh, we still end up with 0, 0, 0. Okay. So those two are redundant, and this example makes it very obvious that those two are redundant. This generates those 2 columns. Multiply this column by 2, you get that. Multiply this column by 3, you get that column. So all we need is this column. And can we simplify it anymore? No, because we don't want to subtract elements from one coordinate to the other coordinate. If we want to end up with a 1, we could by dividing everything by 4. So we end up with 1, 5, 4, 6 4s. I don't quite see the value of that. Well, I don't see too much value really on that. We can just say, hey, we are finished. A basis for a basis for the space. Let me erase A for the space generated by the columns of the matrix is the single vector 4, 5, 6. Yep. That is always going to be linearly independent. If you have one vector by itself, no matter what vector it is going to be linearly independent with its, well, the set with one element in it is going to be linearly independent. Unless we have 0, 0, 0. Yeah, so any non-zero vector will be by itself in a set, will make the set linearly independent. This is non-zero, and consequently, that is linearly, this set is a linearly independent set. Let me write that down. So so this is a fact. Any set with exactly one non-zero vector is linearly independent. If you have the zero vector by itself, that is not linearly independent. Yeah. Yep. That's it. We're gonna finish the video here.